Hello and welcome to The Ruffian with me, Ian Leslie. A few weeks ago, I posted an extract from a brilliant book called A Brief History of Intelligence by Max Bennett. It's one of the most enjoyable and thought-provoking science books I've read in years. The extract I posted is about the evolution of language, and it proved really popular with Ruffian readers. So do check it out if you haven't already. I was delighted to have Max on the podcast to discuss some of the questions his book raises, particularly around the similarities and differences between human and artificial intelligence. In part 1, which is free for everyone and on all the usual podcast platforms, we talk about the concept of reinforcement learning and why it's important to both human and machine intelligence, the differences between how AIs and humans learn, and the evolution of the imagination, of creativity, of the human ability to simulate different worlds, different futures. It's all fascinating, but I strongly recommend checking out that last part of the discussion in particular. In part 2, which is for paid subscribers only, I asked Max about something that he doesn't get into in the book, which is the future of AI. How does his deep understanding of human intelligence inform his thinking about where we're headed? What are the biggest problems for AI engineers to crack? Is AGI, or superintelligence, on the near horizon? And if so, how likely is it that we're all doomed? Amidst all the noise and hype, Max offers a calm, nuanced, and insightful perspective. I hope you enjoy our conversation. Hello, Max.
Hi.
Thank you for joining us. Tell me a bit about your background, because you're not a full-time writer, you're not a full-time academic. What are you? Who are you?
I don't know. Who am I? What a good question. I've spent most of my career building technology, specifically software and AI tools. So I spent the first 8 years of my career building a company called Bluecore, where we were selling an AI platform to really large e-commerce companies. So all of the sort of annoying emails you get from many companies, a large portion of those are powered by Bluecore's AI tools. So we would use, this is pre-LLMs, we would use machine learning models to build recommender systems, figure out what people would be interested in. We'd try to infer what's the right messaging, help companies with segmentation, all that stuff. So that was sort of the beginning of my career in AI. And from there is when I started becoming really, really fascinated with the intersection of why is it the case that AI systems can't do various things that humans can do effortlessly well. And that was the beginning of my interest in the brain. But yeah, my background is in building companies.
Okay, I mean, I have to ask this as a writer of books myself, like, how the hell did you find time to write this immense book? And
yeah, it was my weekend project. I did take a year off to finally finish the book, but during the tail end of my time at Bluecore, I'd say the final year and a half, every weekend I would just be writing. In fact,
well, you must have been obsessed by the subject for years, right? Because it feels like you've assimilated a huge amount of information about the evolution of life and the brain and human intelligence, and that doesn't happen in a year or two. That feels like something you've...
Yeah, it's interesting. I've always been a voracious note taker. So this book did not begin with the intent of even writing a book. I just became really fascinated with the age-old question: how does the brain work, and why is it the case that humans can still do things we can't figure out how to get AI systems to do? And so I just started reading a bunch of books. I had no intent of writing a book at all. Reading pop sci books evolved into reading textbooks, which evolved into reading scientific papers. I ended up coming up with a few somewhat novel ideas on a part of the brain called the neocortex. So then I ended up publishing a few papers, and that's sort of how I began my network into the academic community, where people became mentors of mine. But what ended up happening was there was this gap, what to me felt like a gap, where there was no book that had answered the question from an evolutionary perspective in a satisfying way to me. And so the book, the book we're talking about that I wrote, it started just as notes. I wanted to, I'm over here. I have the, this is the classic John Cass evolutionary neuroscience book, which I have read, like front to back.
That is for listeners who haven't got the video. That's a huge, chunky textbook. Yeah.
Yeah. So I just ended up, going deep, reading all of these textbooks about and papers around what do we understand about how the brain came to be. I mean, the short answer is we don't know a lot, but what we do know is way more than I felt like had been sufficiently succinctly described to a layperson audience. And then I eventually built enough conviction that I really wanted to turn this into something for people. So that's when I took a year off to actually write it. But yeah, it was 3 years of reading, note taking that eventually evolved into deciding to actually write a book.
This is a vastly interesting book with so many dimensions to it. I'm not going to try and talk our way through it because people need to read the book. But I'm going to just focus on a few aspects. And I suppose one of the things, the aspect of it that I'm particularly interested in is learning, which is obviously a huge part of intelligence. And well, let's start with a big question, and then we're going to kind of get into some more specific ones. But throughout the book, you're making comparisons between human intelligence and AI, and one of the questions that you're kind of playing with throughout the book is how they learn. Can you just tell me a bit about how AIs learn what's the difference between the way that humans learn and AIs learn? Or what are the big similarities and what are the big differences?
So we don't actually fully understand how humans learn is the first, but we do understand the mechanisms by which AI learns. So the standard mechanism for learning in AI is something called backpropagation. And, in simple terms, one constructs, by the way, sidebar, how technical is your audience? Because I want to make sure I don't
Not very technical. So.
Okay.
Yeah.
So I'll give high level. Okay.
Yeah.
So, the standard way that AI learns is through an algorithm called backpropagation. So you can imagine in your head sort of a web of neurons. You've probably seen pictures of that on the internet. And what we do is we give training data. So with the standard approach, something called supervised learning, where you have a set of inputs. Imagine it being pictures of cats or pictures of dogs. And then in the beginning of the network, at the end of the network, you have some numerical representation of a label. Let's say it's a text field that says cat or dog. It could be a number or whatever. And what you want to do now is you want to train this network to receive images of cats or dogs and predict whether or not it is an image of a cat or a dog. And so the way you do that is you give a ton of data of cats and dogs with the correct label. And the learning algorithm is something called backpropagation, where in simple terms, you pass these numbers through the network to the end of it. And then at every one of these sort of connections, you can compute what is the relationship between the weight of that connection and the error at the end. Without getting into all the detailed calculus, that algorithm works remarkably well, meaning that if you pass enough data through it, over time, the network gets better at producing the correct output. And so people have tried to find alternative learning algorithms to this, especially in the neuroscience community, for the simple reason that it's very hard to understand how a web of real biological neurons could possibly do something like this. Because in order to do backpropagation, you need to imagine a web like 100 layers of neurons. The math that you're doing is on layer 13. You are figuring out exactly the relationship between the weight between one neuron on layer 12 and layer 13 and the error at the very end of the network. And there's no biologically plausible, like, some people have come up with approaches, but there's no consensus on how a biological web of neurons could possibly do something like that, although there are some emerging possibilities. So mechanically, there seems to clearly be something different, or at least there's the big community of people in the computational neuroscience community that agree that there's got to be something different going on between these systems. More abstractly, though, what's fundamentally different, which I think is maybe more practically understandable, is the way we train AI systems is we give them a huge quantity of data pretty much all at once. So the way you actually train these systems is you take a huge data set, you batch it, and then you shuffle it, and you keep funneling it through the system where it sees the same data over and over and over again until its performance gets good. And then when you release it into the wild, it doesn't learn anymore. So as you're talking to ChatGPT, they're not updating the weights of the underlying model. Now, it does feel like ChatGPT is learning, and we can get into how they're mocking the process of learning, but the underlying weights of that model are not changing. And we don't do that because when we let AI systems learn continually, their performance degrades rapidly. In contrast with a human, and really all mammals, or many, many animals, we only receive a stream of information. We are not trained on batches of data the way that an AI system is. We only receive a continuous stream of data, and yet we do not somehow catastrophically start degrading our performance on old tasks in the way that AI would. A simple example is when you learn how to drive, you don't forget how to ride a bicycle. And so this is sort of one of several of the key differences between AI systems and human learning systems. And we don't really understand how it is that humans are so good at what's called continual learning, and AI systems are not yet. Some people believe that the sort of the last big hill to climb to AGI is this continual learning problem.
And is it right to say that humans are learning from very small bits of information? They're doing a lot with a little. They're learning to generalize from examples in a very kind of economical way, in the way that AIs need a lot of data in order to learn something.
Yeah, maybe a simple way to articulate exactly that point is we learn everything we learn reading, the sum total of maybe a few thousand books by the time you're 20. And ChatGPT, to get as good, had to read tens of millions of books, right? So the amount, the consumption of data is on a totally different order of magnitude to get to similar performance. And so what people think is there's something different about the learning algorithm that makes us materially more efficient learners than these AI systems.
But we're both doing pattern recognition. Is that right? We're just doing it in a different way.
Yeah, the ways in which we're similar is there was a whole movement in AI. I mean, a lot of these things are still open for debate, but there was a whole movement in AI in the 80s on what's called symbolic systems, which is effectively trying to get systems to be smart through direct programming, right? So programming logic into these systems. And there was another movement which was around statistical learning, which is what was called connectionism, which is now just neural networks. And it seems silly in retrospect because neural networks worked so effectively that it's hard to imagine. But back in the day, it wasn't obvious that getting a system to figure out how to compare pictures of cats and dogs just by showing it a bunch of examples and learning the statistical regularities of what's a cat and a dog, where it will never be 100% accurate, versus a system that logically deduces what exactly makes a cat versus a dog and then, renders an opinion at the end. A lot of people would have said the logical deduction is the one that's going to perform better.
Yeah.
But in retrospect, what ended up happening is the statistical regularities, that approach ended up being much more general and ended up working much more effectively. Human brains, in some ways, are combinations of both of these, but the foundation of our brains, pre-language at least, is clearly statistical learning. There's no good evidence that monkeys, non-human primates use symbols the way that humans do, and thus the foundation of our brains is really in the category of the statistical learning connectionism. And so in that sense, there is a lot of similarities in the way that AI systems that have worked really well work and how human brains work.
Can I ask you to just draw that point out a little bit more, because I didn't quite understand it? Why does the fact that we use language and our nearest cousins do not imply that we are learning on the basis of a statistical?
Oh, it's the opposite. Sorry. What I'm saying is the most ignoring language, so ignoring the feature of language, which can be argued to be a form of symbolic learning. Everything that humans learn and non-human primates learn is effectively statistical learning, which is the same way that AI systems learn. So we receive a stream of data, we build a predictive model of them, and we're doing our best to predict what's going to happen next, or the best set of actions that achieve some outcome. That is not a logical deduction. It is a sort of statistical exercise. That's how pretty much all animals learn. There is this odd exception that evolved in early humans where we developed language. And language enables us to do a form closer to the type of symbolic learning that was, So most learning in animals is physical learning. Yeah.
Okay. Yeah. So before we get into language, which is a pretty newfangled technology, right, in the great evolutionary scheme of things, kind of like the iPhone of evolution. Let's just stay pre-language a bit and talk about reinforcement learning, which is this process which I guess is kind of driving the statistical inference. Tell me about its significance on both sides of the equation here. So for humans and for AI systems.
So, one interesting thing about the more one learns about the human brain is it's pretty clear that there's not a single learning algorithm being implemented, at least at the scale of networks of neurons. Maybe at the scale of individual neurons, there's common learning mechanisms. By which I mean that the human brain contains something akin to a reinforcement learning algorithm within it, but that doesn't encompass everything or all the ways in which the human brain learns. So I'm sure we'll get into this, but for example, the part of the brain called the neocortex, the foundation of the way the neocortex learns doesn't seem to be about reinforcement. It seems to be around predicting things, predicting the next state of the sensor of what the sensorium, what's going to happen next, and the error that it learns on is its prediction error. How good is it at predicting what's going to happen next? And when it's poor at predicting, it tries to update its model, which is different than part of the brain called the basal ganglia, which literally what it tries to do is take a set of actions that maximizes the release of dopamine. And we are a brain that has paired these things together, and they work in symbiosis with each other. So just to make that claim. Okay, so reinforcement learning is a really interesting story because the story of reinforcement learning is one where it's very intuitive, but the more AI systems had attempted to actually build reinforcement learning into real algorithms or real robots, we learned that it was actually way harder than we thought. And the challenges in building systems that actually learn through reinforcement provided insight on how the brain actually works. So it's a really cool story of the symbiosis between AI and neuroscience. One of the very early movements in psychology was something called behaviorism.
Yes.
And in behaviorism, the idea was to try and understand the bulk of animal and perhaps even human behavior through the lens of effectively reinforcement. This was classically called, invented by this man named Edward Thorndike. And he came up with this idea of the law of effects, which is effectively things that get reinforced become more likely to happen. Things that get punished or result in pain become less likely to happen. And of course, with a bunch of animal experiments, it's very clear that you can get animals to change their behavior by giving them reinforcements. Same thing with punishments. So the theory was a huge portion of learning, perhaps all of learning, the extreme versions of behaviorism believed it was all of learning, can be explained simply by things that lead to good outcomes just become more likely to happen. Things that lead to bad outcomes become less likely to happen. And maybe all of intelligence is just that. So that makes a lot of sense.
Yeah.
Seems very intuitive. Then we tried to actually build an algorithm that does this. And so this, there's some early examples in the 50s. An early example that I like is something called Snark, which is a little algorithm invented by this man named Marvin Minsky. And effectively, it doesn't work. If you try to train an algorithm to just do a basic thing like play a game of chess or chess isn't simple, play a game of checkers, get out of a maze, and all you do is you let it take random choices and you give it a little reward when it does what you want, and then you have it play again, and because more likely to do the thing that led to the reward, it doesn't actually get very intelligent. It doesn't really solve the puzzle. The reason is something that Marvin Minsky identified called the temporal credit assignment problem. The issue is that when something good happens, so suppose you win a game of checkers and you get a reward, what prior action actually causally led you to win, led to that good thing? If all you do is reinforce the things that happen just before the reward, you're not going to get very smart, because it might be the case that the reason you won the game of checkers was some really smart move very early in the game, and then the rest you were certainly going to win. It was just sort of playing out the motions. And so this was largely an unsolved problem for decades. And then this brilliant man named Rich Sutton came up with a very, very clever idea on how to get this to work in AI systems. And he actually studied psychology as an undergraduate, so he was very inspired by the questions in natural intelligence. And the idea is elegantly simple. Perhaps the way to train an AI system to learn through reinforcement is not to just give it a reward at the end of the game, but to have it always have a running expectation as to how well it's doing. So in other words, imagine we're playing a game of checkers, and I don't only get reinforced whether or not I win at the end of the game, but every move I predict how likely am I to win. And my reward is the difference between my likelihood to win in the prior move, the prior state of the board, and the current state of the board. In other words, if something happens on the board that all of a sudden improves my chance of winning, that's when I feel the reinforcement. And we all experience this when something happens where all of a sudden we realize, oh my God, I think I'm winning, or oh my God, I think now the game is over. That's the moment we feel something.
So it's the pleasure of anticipation.
Exactly. Yes.
Yeah.
So now that's very simple, but in practice, it's not clear that would work, because these systems are bootstrapping on each other. My ability to predict how likely a board position is to me winning is contingent on what moves I'll make. And the moves I make are contingent on the reward I'm going to get based on my prediction on whether or not the board position is good or not. So these things, it's a little bit circular. But when you actually train these systems, it works. And this is something called the temporal difference learning. This has become sort of the foundation of reinforcement learning. It's used in modern RL systems all over the place. And so that works, which is having one side of the model, which is predicting the likelihood of future reward, and the other one that is rewarding the system based on these fluctuations. In the 90s, it was discovered that dopamine responses align almost to a T. Now there's nuances that have been discovered, but almost to a T to the temporal difference learning algorithm. Dopamine is not fundamentally a pleasure signal. It is an anticipation of future pleasure signal. It is something that is released when the predicted state of the world gets better, and it is sucked out of certain parts of your brain when the predicted state of the world has gotten worse. And so that's this beautiful synergy where we in AI, we realize in order to get a system to work, the reinforcement signal should not be the pleasure signal. It needs to be based on a predicted future reward. And then when we looked into brains, we realized it seems like that's how brains work. And it's not just human brains. We've seen that signal in mammal brains. It's way less studied. There's I scoured, the literature to try and find papers on this. We don't really know the extent to which this exists outside of mammals, but some early research suggests that fish brains work exactly the same way. They have the same basal ganglia structure that predicts these reward signals. So the evidence points to the idea that this temporal difference learning mechanism evolved in early vertebrates hundreds of millions of years ago and is shared across fish all the way to humans.
And the work that uncovered that the truth about how dopamine works, that was influenced by the AI discovery. Is that right? So this is kind of two fields learning from each other.
Yep. Yeah. I mean, there was people were trying to understand these perplexing dopamine responses. And then there was this sort of bridge to the realizing, well, this actually aligns to this emerging algorithm in the AI community called temporal difference learning. And then it was discovered these are actually, very aligned.
Amazing. You talk about the role of curiosity, something I'm particularly interested in, having written a book about it. Can you just expand on why curiosity is important in the light of the process we just talked about?
Yeah. So I'll take a similar approach because I think it's how my mind works, and I think it is cool. So once we had this discovery of TD learning, temporal difference learning that we were just talking about, people started applying it to beat all sorts of games and all types of sort of interesting games that were previously hard to solve. People found ways to solve with various variants of TD learning. But there were certain games that you still could not beat, despite the fact that humans could beat it. And the one classic example is a game called Montezuma's Revenge, although there was many games that TD learning can't beat. And Montezuma's Revenge is a very old game, but what makes it hard and challenging is you start off in a room and there is no reward for a very long time. So you have to go to different rooms, you're exploring all these things, and the first reward is many, many rooms over. When you finally get to level 2, you just open a door and then you escape. And so TD learning doesn't do very well when the rewards are super, super sparse. Because what ends up happening is the system will just get stuck in a loop. There's no signal on which to go as to where it will. It never escapes level 1. It never learns to go all the way to the faraway room to escape. Unless you imbue the AI system with something quite familiar called curiosity. And so this is classically called, this is a dilemma. This isn't just something with Montezuma's Revenge. It's called the exploration-exploitation dilemma. And so you could think about it not only in the context of Montezuma's Revenge, but also in a game of chess. So suppose we play a game of chess and I win. Do we think that all I need to do now is just repeat all of the moves I made in that first game? In other words, exploit the reward signal I have now learned? Or is it possible that there was a better set of moves I could have made in that game that would have allowed me to have a higher likelihood of success? If all I do is repeat things that previously worked, I'm always at risk of missing things that could have been better. And so that's the dilemma between we can exploit what we know, but there's always this risk that there's better things, more safety, more reward to be found if we try different things. That's
anybody who's been through the dating process and looking for a romantic partner will understand the principle.
Right, exactly. So when you imbue these an AI system with simply a reward for new things. So what you do, this is the sort of algorithmic manifestation of what we would call curiosity. So this AI system, all it does is just predicts the next sensory state, and it gets a reward when something surprising happens. So now this AI system has sort of two dual goals. One goal is to exploit rewards that it knows, that it's learned, but the other is just to surprise itself. And so what does the system do in the game of Montezuma's Revenge? It starts exploring new rooms. It gets bored of a room that it's tried all of the action. It no longer is stuck in these loops that the first system would. It goes to different rooms. When it's bored with that room, it goes to the next room. And eventually it gets out of level 1 because it does what a human would do, which is it explores. And so this is something we have found all over the case in, solving certain sparse reward challenges in reinforcement learning. And of course, we see curiosity all over the animal kingdom. Curiosity is fish show curiosity all across vertebrates. Many invertebrates also show curiosity. It's clearly a foundation of being an agent in a world. It's a sort of fascinating. It's a fascinating second synergy between AI systems and natural intelligence systems.
Totally agree. Although one of the questions it raised for me is why the AI systems as we have them now, the LLMs and so on, do not seem more curious. I mean, they don't seem curious to me. They just sort of sit there passively waiting for you to ask it questions.
So interesting. I mean, we do not train, for the most part. There's some nuance in this, but we don't train large language models with reinforcement learning. The foundation of training these large language models is effectively supervised learning, where we just show it a bunch of text and we try to get the system to predict the next token or the next word that's being produced. And we curate these very, very, secretive, because this is where all the IP really is for these companies. We curate these amazing data sets and we train these systems in the right order to get them to do what we want. But this is one of the main critiques of these large language models, even when framed as AI agents, meaning they can make API calls and things, is they're not actually, they didn't come to be in a world where they had to interact with the physical world, where there were consequences of its actions and had to learn the consequences of their actions. And so, there's open questions on whether that matters and whether AI agents will still be able to get to superhuman intelligence or this is going to be sort of a fundamental roadblock. But yeah, large language models are not trained the way that a standard RL agent would be trained.
Okay. Yeah, that's interesting. All right, so let's move on to a couple more kind of huge questions that I'm throwing at you, and you're dealing with incredibly well. Thank you. Why was the cortex in early mammals so important? And as I understand it, this is the point at which we start to not just learn by trial and error, but learn by simulating trial and error. In a sense, this is the kind of birth of the imagination. Is that a kind of fair glib summary of what's
yes
going on?
Yeah, so we've always this is where the evolutionary story became so fascinating to me, and this is where I sort of came to the conclusion I couldn't forgive myself if I didn't go through the process of writing this book, irrelevant to what happened with it. Yeah. So if all one does, which is sort of the standard approach in neuroscience, if all one does to understand the human brain is go into the human brain and try and understand how it works, one of the very obvious conclusions that happens is the part of the brain called the neocortex is very, very important. And the reason you come to that conclusion is because if pretty much any part of your neocortex, with a few exceptions, gets damaged, there's catastrophic degradation in your ability to live in the world. The back part of your brain, your neocortex, is where clearly visual perception is fundamentally happens in humans. You get damage there, one becomes effectively blind. Control of your body is part of this neocortex called the motor cortex. There's part of the neocortex that is causally related with speech. So when you look at the human brain, you go, well, all intelligence is just neocortex. But from the evolutionary perspective, it's hard to come to that conclusion because the neocortex has not always been around. And if you look at other non-mammalian vertebrates, so the neocortex evolved in early mammals. So you look at a fish brain, you look at reptile brains, even look at bird brains. They don't have a neocortex, and yet they're eminently able to do many, many different tasks. So there's this interesting the question as to what drove the evolution of this thing called the neocortex when animals seem to be quite intelligent without one. And yet on the mammalian lineage, this part of the brain that didn't exist exploded into the locus of everything not everything, but many, many things that humans do: motor control, planning, visual perception, etc. And so one way to answer this question is to try and tease out through comparative behavioral studies what seems to have evolved from from the perspective of capability in early mammals. So what is it that early mammals seems like they garnered the ability to do that earlier non-mammalian vertebrates could not do? And this is obviously hard to answer because convergent evolution happens all the time. So, an example of that is lens-shaped eyes evolved independently many times. Wings evolved independently many times. So what that means is you can't just say, let me just look at what a few mammals do and compare it to a few non-mammalian vertebrates and deduce, the state in the past. For example, birds became intelligent through their own lineage, through their own brain mechanisms, and birds are not a good example of what our ancestral vertebrate was like. Okay.
Yeah.
All that said, without boring people with all of the details, it seems to be the case that on the transition from early vertebrates to early mammals, it was not the ability to have curiosity, learn through reinforcement, have pattern recognition. You see all of those abilities eminently well in non-mammalian vertebrates. But what early mammals seemed very good at is not only engaging with the world by predicting the next state and maximizing reward, but also being able to pause and imagine possible future states or past states of the world that are not the current one. In other words, to imagine. There's some really beautiful studies that show even rats will pause at choice points in mazes and imagine future paths. Rats will pause after making a choice, and you can literally go into their brain and see them regret their prior choice and imagine taking an alternative past. They're really cool studies that demonstrate this.
Yeah.
And there's no good evidence at all that non-mammalian vertebrates, with the exception of birds, are capable of doing something like that.
Yeah.
And
Just to, I mean, I do think this is a really fascinating point, and you could see. So these rats will kind of get to a junction. It's like, do I turn left? Do I turn right? And you can actually see them simulating going left and turning right, or turning right and then making the decision.
Yeah, so there was a discovery in the 40s that rats would, when navigating mazes, they would pause at choice points specifically when the experimental setup was such that it wasn't obvious which direction one should go. Maybe you're changing the directions, maybe the signal is ambiguous, so on and so forth. And rats would look back and forth before making a choice. And so that doesn't prove anything, of course, but psychologists hypothesized, some did, that this was something called vicarious trial and error. In other words, they were vicariously imagining themselves take different actions and rewarding themselves in their mind when a good thing happened and punishing themselves in the mind when a bad thing happens. In other words, going through the process of trial and error, but not in reality, vicariously.
Yeah.
But there was no way to prove that that's what a rat was doing. So this became sort of like a pet idea that, because it wasn't grounded in anything experimentally verifiable, nothing really came of it. Until the early 2000s, David Reddish's lab at the University of Minnesota effectively discovered that rats are doing exactly that at choice points. So there's a part of the brain called the hippocampus. Without getting into all the detail, there are certain neurons that activate at certain locations within a maze. So typically, those locations are the location that the rat is actually in. So as a rat's moving, you can see these place cells activate as they're moving around, and the place cells represent their current location. But specifically at these choice points, the place cells cease to activate in the rat's current location and start making these forward sweeps into the directions that it's looking. So you can literally watch the rat imagining its possible choices before acting.
It's incredible.
Which is amazing, yeah. And you can do it in different parts of the brain too. There's a part of the brain called the orbital frontal cortex that you can differentiate imagining eating different foods. And so David Reddish's lab also did experiments on rats where they have to make choices between different foods. And if the rat, you can do the experimental setup such that if it makes a certain choice, it would regret its choice because it has to wait a long time for a certain food. And you can watch the rat imagine eating the banana that it could have had if it didn't make the wrong choice. And you know it's the banana because you've gone to the orbital frontal cortex and you've parsed out which neurons represent banana versus chocolate versus raspberry, as an example. So there's been several studies that demonstrate this existence of imagining a state of the world that's not the current one in mammals. And so that's an incredible new ability that over the mammalian lineage, the part of the brain that was really this specialized tool for imagining not the current state of the world, slowly expanded into being the locus of intelligence. We humans live in this mental simulation, whereas a rat maybe mostly lives in the moment, but has these specific situations where it will render these future states of the world. But the core of what the neocortex does is it's meant to render an entire universe in your head for the sole purpose of being able to re-render past events and imagine possible future events.
Incredible. And physically, it's biologically, it's the same structure. I mean, all of the neocortex is the same, but it can perform very different functions. It's just using the same material in a different way.
So the one of the first things that made me really fascinated with neuroscience, which I think has enraptured many people because it's such a fascinating sort of discovery. Jeff Hawkins' class is one of the current most famous people talking about this, but this has been something that's been known for many decades. Is that we look at the human neocortex. And it seems to do many different things, right? There's a part of the neocortex that seems to be related to language, another one for vision, another one for music, another one for audition, so just understanding sound, another one for movements, planning. So ex ante, one would think these different regions that do these different things must look structurally totally different because the algorithm that's needed to recognize visual objects certainly is different than the algorithm needed to speak or move. But when you look at the neocortex, it looks, people will debate small differences, but the most notable thing about the neocortex is how similar it is everywhere. The part of the neocortex that does language doesn't look fundamentally different at all than the part of the neocortex that does vision. And there's a famous study that really emphasized this, where they took ferrets and they rerouted the visual stimuli, so the flow from the retina during development, towards the part of the neocortex that should have evolved into the auditory cortex. So the idea is, what happens if you reroute incoming visual input not to the part of the neocortex that typically does vision, and you route it to auditory cortex? What effectively happens, auditory cortex just became visual cortex. Yeah. And so what that suggests is that the neocortex largely just does one thing, and what differentiates two regions is just what inputs it receives and where it sends its outputs.
It's the simulator,
right?
Yeah.
So it renders a model. So what's not very controversial in neuroscience is that the neocortex is rendering a predictive model of the inputs it receives. So it's trying to render a model of a rich enough model of the input it receives such that it can explore that model. So an example is the visual cortex is it receives a ton of visual stimuli, and it tries to construct a rich enough model of visual stimuli such that you can close your eyes, imagine a 3D object, and rotate it in your mind. Right. And that's a very unique type of model because it needs to be able to receive simulated actions on an object or one's own action and be able to predict things about visual stimuli it's never received before. So it's classically called generalization. You should be able to generalize very new things. And so it seems and some people are really fascinated with this because it suggests there's some general intelligence algorithm being implemented in the neocortex that can be applied to so many different modalities. And so if we could only figure out what it does, we could apply it, right? So I, spent a whole 6 months fascinated with this, published a paper on it. Of course, no, I still don't understand it. We don't know. Jeff Hawkins has some really fascinating writing on, and they have a really interesting research program on this. There's other, there's a whole what's called predictive coding research program on this. So a lot of people are working on it. We don't really know exactly what the algorithm implemented by the neocortex is, but it's fascinating to try and figure it out because obviously there'd be many applications of it.
Is there something distinctive about the human neocortex versus other animals, other primates, or is it basically the same?
So this is an age-old, hotly debated question, and it comes down to effectively how different do two things have to be given the label different, right? So every human brain is slightly different. Like they're not exactly the same, obviously, because we're different people. And so what I find most striking, and I would think anyone who's not stoked in sort of academic, deep, nuanced debating would think when they first learn about the differences between a human neocortex and a non-human primate neocortex, is how these things are almost exactly the same. They are extremely, extremely, they have the same layers. They have pretty much the same connectivity. We have yet really defined, there's maybe like one or two regions that could be called unique to humans in the human neocortex relative to non-human primates, but that's even hotly debated. The part of the human neocortex that does language is in fact found in chimpanzee brains. It just doesn't do language, but the connectivity is pretty much the same. So people still are hunting for, like, is there a unique neuron in the human brain? Is there maybe, so there's some theory that the connectivity between the two regions that typically do language, called Broca's region and Wernicke's region, although they exist in non-human primates, there's some possibility that the connectivity between them is deeper in humans, and maybe that unlocks something. All of that's possible, but the most striking thing is that the line between humans and non-human primates, at least biologically in our brains, is very, very thin. One would think you would go into our brain, you'd see a completely new region, you'd see a totally new neuron, you'd see a totally new layer. We don't see any of that. If there, whatever differences there are, they're either just of scale. We do have way more neurons than a chimpanzee brain, or it is a minor shift that has a minor physical shift that has a large impact on behavior, right? It would have to be something like that.
Yeah. What about mentalizing, thinking about what others are thinking and what they're doing? That's something that we seem to do better than other primates, but they do it too. But we seem to do it on another level.
So this is another really fascinating area of the literature, which sometimes comes down to, nomenclature. You'll see funny things like, what's the definition of episodic memory? And because it's so loaded with things, like the literature on non-primate mammals will typically refer to the discovery of an animal's ability to take different choices based on recent past events as episodic like memory, because no one wants to include a lot of the baggage associated with the term episodic memory. So within mentalizing, yes, there's depending on how you define these different features, you can draw lines to different places.
Yeah.
But I think if one key aspect of mentalizing is something called theory of mind. And if one defines theory of mind simply as being able to take different actions based on what it seems to be the other agents, so typically someone in your family, friends, their intent is, or their knowledge, being able to make different choices based on what you think their knowledge is, you think their intent is, being able to take actions to change their intents or change their knowledge, then there's a lot of evidence that non-human primates can do that effort very well. And they seems to emerge from parts of the brain that's also where mentalizing happens in human brains. And those parts of the brain uniquely evolved in early primates. So all that evidence points to mentalizing probably emerged in earnest in early primates. I'll give you a few sort of studies that demonstrate this. So a classic theory of mind test in humans is something called the Sally-Ann test. And the Sally-Ann test is, you have two baskets and you have Anne, I forget if it's Sally or Anne, but Anne is in the room and she puts a ball in basket one And then Anne leaves. Sally comes in and moves the ball from basket 1 to basket 2. Sally leaves. Anne comes back. Where does she look for the ball? Now, children before the age of around 4, it's different for different children, don't understand the notion that another mind could hold different knowledge than your own mind. So they will always predict that where Anne will look for the ball is in the bag, the basket where it actually is, because that's what the observer knows. But around the age of 4, children will realize, well, Anne never saw the ball move. So Anne will think it's in the original basket.
Yeah, she has her own mind.
Right, she has her own mind. And you can do these types of tests on chimpanzees, and they show the same. They show the ability to recognize where other people will think something is, even though they know it's not there. You can do this just based on gaze following. So you can see they will look where they anticipate the person's going to look for something, even though the chimpanzee knows it's not there, but they anticipate the person's going to look there for the thing. And that ability goes away if you do something called TMS, transcranial magnetic stimulation, which just inhibits part of the brain. If you do TMS to the part of the brain that we know is causally related mentalizing, chimpanzees lose the ability to do that. They no longer have the gaze bias towards where someone thinks someone is. There's also lots of other funny chimpanzee studies on this where chimpanzees can differentiate between intentional and accidental actions, which is very hard to imagine how this happens with classic RL. So an example of this would be, suppose chimpanzees learn that 2 boxes enter a room, and the box with a red marker mark on it always has the food, and the one that does not have the food. So now in their mind, standard RL system, red marker equals food. So now have a human come in, and a human goes down and intentionally marks one. So you see them bend over and mark it with a marker, and then looks away and drops the marker on the other one. So the marks are identical now. The only difference is one was intentionally marked and the other was accidentally marked. Chimpanzees can effortlessly go to the one that was intentionally marked. They can tell the difference between these two actions. You can do that same thing with the ability. Yeah, there's lots of different experiments like that demonstrate that chimpanzees can differentiate other people's intent. And so there's some really interesting sort of evolutionary history as to why that evolved in early primates that we can get into. But that seems to be one of the key intellectual breakthroughs that occurred in early primates, is the ability to reason about other people's minds.
I like the Machiavellian theory that they basically evolved that in order to trick and deceive.
Yeah.
So what I love about the story you're telling and the way the book works is this thin sliver really between human brains and other animal brains and primate brains in particular that makes such a huge difference. But yeah, let's focus on what does make a difference. So we'll talk about language, but also just want to talk a little bit briefly about joint attention and why that's so important.
Yeah. So the two features, so I should just always make the disclaimer that, like, one of all the things that are hotly debated, one of the most hotly debated things is language in humans and non-human primates. This has a ton of academic baggage here, where there's a whole camp of people that claim that non-human primates have some semblance of language. There's a whole camp of people that think that language is not what makes humans unique. Language is an outgrowth of some recursive algorithm that makes humans unique, and so language is in the foundation. So just to say that, there is controversy around here, but the story I tell is the one I find most convincing, and I think most of the evidence points to. But just that disclaimer. Okay, so the two features that I think are most convincing that are unique about human language is this feature of declarative labeling and this feature of grammar. Declarative labeling is this notion that you can assign a label, so think about it as a word, dog, to a thing, dog, and share that label with other people. And that's different, and linguists draw a distinction between a declarative label and an imperative label. An imperative label is, I hear a stimuli, a label, And I know if I take a certain action, I get a reward. So an example is a dog learning sit. A dog learns if you say sit, if it sits, it will get a reward. That doesn't prove that it has the notion of a declarative label. It understands the notion of sit. It just knows that when I hear this symbol, if I take an action, I will receive a reward. And so differentiating behaviorally between the existence of declarative labels and imperative labels is challenging. But with humans, clearly we have this notion of declarative labels. We assign labels to things and we can share in them. How does that come to be? And so if you actually look at human children, one of the most interesting features that is associated with the ability to learn declarative labels is pre-verbal infants do things that it's very hard to get non-human primates to do, which is something called joint attention, where if you have an object, a human infant will go to a lot of effort to ensure that they and their parents, typically their mother, are attending to the same object. So an example is an infant will point to something or hold something and will go back and forth checking their mother's eye gaze to ensure that they are gazing at the same object. And they've done lots of studies to try and prove that the infant's objective is not to get anything. So it's just they're satisfied simply by ensuring that their mother or father is attending to the same object. So this instinct to want to engage in joint attention is the instinctual algorithmic foundation for declarative labeling. Because if you can ensure a hard-coded algorithm in our brains to ensure that other people, specifically parents, are attending to the same thing, then it's not hard. The next step is simply that the parent has to make a claim, make a word, say a babble, that can be assigned to that thing. But if there's no way where we can make sure we're thinking about the same object or action, then it's very hard to assign labels to things. And this is what's challenging about training non-human primates on language, that it's hard to ensure that they're attending to the same thing as us, as opposed to just trying to do actions to get rewards, right? So they're just like, you can tell, the same way you're training a dog, what do you want me to do to get my treat? Is different than get a chimpanzee simply to attend to the same thing, go back and forth, confirm we're attending to the same thing, and then assign a label to it. And so joint attention, and there's been lots of interesting studies showing that there's a strong correlation between the degree of joint attention and the speed of language learning, and there's the whole literature on that. So declarative labeling is one feature of language, that there seems to be a unique instinct for joint attention in early humans that enabled that, which non-human primates don't have, which again, it goes back to what we were previously saying on small biological changes might have huge behavioral impacts. So this doesn't mean it's a unique learning algorithm, just adding the instinct to engage in joint attention. So that doesn't require any changes to the neocortex. That's a deep, maybe an amygdala, old brain type thing that just changes an instinct for something, enables a totally new feature like declarative labeling. And then the second is grammar, which is more hotly debated, and of course, and grammar is this idea that not only are there declarative labels, but we learn the structure of the way in which you order these symbols conveys meaning. And it doesn't seem to be the case that non-human primates, even when there's been studies that maybe suggest some declarative labeling exists, the grammar of the utterances they make is extremely limited, whereas humans can construct totally novel sort of sequences of labels, and other humans will understand what they mean, even though they've never heard any sequence quite like it before. And so, so declarative labeling and grammar are two sort of key features of language. We have a better understanding as to how declarative labeling emerges. Grammar is more hotly debated. One open question is whether grammar is something that's accessible to any neocortical powered brain. It just requires the foundation of mentalizing, and it requires declarative labels to come to fruition. Or some people argue what we were saying before, that unique connectivity between Broca's area and Wernicke's area is what allows for recursive grammar. There is an open debate around that.
And declarative labeling, so it is built on this foundation of joint attention. And and that then those two kind of work, and I suppose in a loop, because that's the foundation of collaboration, right? Being able to organize and do things together with intent. I mean, I love what Michael Tomasello, the neuroscientist, said. I think he said, nobody's ever seen two chimpanzees carrying a log together. Like, just very kind of basic collaboration is really kind of out of reach for them because they don't have this capacity for joint attention, which then becomes kind of accelerated hugely by labeling and by language.
Yeah, I think one framework I talk about in the book that I find useful is one could cast the evolutionary trajectory of the human brain through the lens of progressively expanding the aperture of data sources for learning. So in early vertebrates, the main source of flexible learning was one's own actions. That's the foundation of temporal difference learning. When I do a bunch of things and when something good happens, I'm going to modify my future behavior. With early mammals, we expanded the aperture, so early mammals can learn from actual actions, but they can also learn from their own imagined actions. So by virtue of building a model of the world, I can now learn from myself, because if my model of the world somewhat well mirrors the real world, I can take vicarious actions in my head and learn from their outcomes. So that expands the aperture. Mentalizing, so being able to reason about the intent of others, further expands that aperture where I can learn through imitation. So when I see someone using a tool, because I can understand their intent, and there's some interesting AI research on this we could talk about, but because I can understand their intent, I become much better at imitation learning. In other words, trying to mirror the actions they're taking. So non-human primates do this all the time. There's lots of studies that show imitation learning. But even that is limited because I'm not learning based on what the other being is thinking about. I'm just learning based on what I see them do. And what language enables is sort of the final expanding of this aperture, where not only can I learn from your actual behavior, but language enables you to share what's going on in your head, and for me to learn from your own inner assimilation. And so, the practical benefits of this are multifaceted. One is, you go into the jungle, you see 3 buffalo over there, you come back because you couldn't hunt them alone. But if you could translate to me, there are 3 buffaloes over there. If you 5 individuals come with me and we all coordinate, we can go get one of these buffalo. If you have the ability to translate that concept, that existence of a buffalo to me, all of a sudden now we can collaborate. I can learn a fact that I wouldn't have known otherwise through you translating that to me.
And you're doing it like incredibly economically and efficiently and fast. I mean, you could take them over to the buffalo and show them, and then go back to the others and
Correct.
do the same thing. But you're just doing it in a few seconds.
Totally. And one can construct their own vicarious plans. So you can say, okay, you could sit down and imagine various strategies of how a team of 3 could hunt an animal. Fail 100 times in your head, find the 101st time a strategy that works for you, and then you could describe in natural language what the 3 of us need to do. I'm going to whistle 3 times, you go north, I go south. You can do all of that, which is not possible, of course, without language. And so that's what many believe, and I believe, makes language so powerful, which is it tethers our inner simulations to each other in a way that's just not feasible without it.
Okay, yeah. So it's really what's wiring us together, and that is the point at which really, well, we're all guessing, but we kind of leap out ahead from the species pack, as it were. I mean, I liked what you, almost as an aside, you said maybe this is the real singularity. We talk about AI and the intelligence explosion and what's to come, but on the long view, actually, it's language, and then everything happens for millions of minutes.
Singularity already happened.
Yeah, that's it. We're just in the middle of it. It's language driven, really.
Yep.
Okay.
The coolest thing. Sorry, just one. The coolest thing about language, or one of the coolest concepts, which I did not invent, there are lots of people talk about this, is that language turns our brains from just a biological organ for a single entity's survival into a medium. The same way that genes became a medium for information the second they became the encoding of protein production in a cell. And the reason language does that is because an idea, a concept, can hop from brain to brain, generation to generation, and it can shift in complexity, it can be added to, it can expand. And so all of life has been sort of stuck in the state where the sum total of information that can exist across generations is just the sum total of information that can be acquired within one lifetime.
Yeah.
But language allows information to propagate across generations. This is why when language evolved, it wasn't like all of a sudden there were cities. It took time because, but it was only a matter of time, because once ideas could propagate from person to person, from group to group, it now a new version, a new abstraction of evolution was created, the evolution of ideas. And that's sort of on the long view, to your point, that's why the singularity already happened.
Beautifully put. Thank you. And just to kind of round off this part of the conversation, how did you feel about the brain after having written your book? It's kind of a strange question, but did you feel like you really understood it at a much deeper level than you had before you dived into this? Or were you kind of still baffled by it, or kind of a bit of both?
Both. I think I feel deeply satisfied with the extent with which I feel like what before was something that was so beyond comprehension. Now I feel like I have some arms around, but I am equally baffled by how far we are from actually understanding how it works. So both these things are true. It's almost like if we're climbing Mount Everest and Mount Everest is understanding, I feel like we got to the first base camp, and that's satisfying. We made progress. I'm happy we're there, but we're far from the summit.
Amazing. Okay, well, look, thank you very much, Max. We're going to wrap up this episode, and we're going to record a part 2 where we get into a bit more into AI and current developments in AI and in intelligence. But for now, thank you very much.